Welcome to this new tutorial in R on how to perform linear regression, both simple as well as multiple linear regression. As usual, let's get straight in the video, and as usual, we will start by loading a few libraries. I won't be going into what each package does, but I've commented out um, what each package does in brief. The last package is extremely useful for people like me. I kid, of course, but it is extremely useful and it will save you a ton of time. And for the purposes of this tutorial, we'll be using the oranges dataset. And if you run this code, $oranges or alternatively help oranges, you will get a description of this dataset. Now, this is a data set on the sales of two varieties of oranges. To keep it simple, we'll be concentrating only on variety 1, but I encourage all of you to, as a practice, to try it out with variety 2. So what variables do we have? Let us quickly load the first 5 rows of our dataset. The head df is the um, syntax for it, and we can see store, day, price 1, price 2, sales 1, sales 2. So we are disregarding price 2 and sales 2 because we are only concentrating on um, price 1 and sales 1 of variety number 1. So the store variable is a factor or a categorical variable with levels 1 to 6, and they denote the store that was observed. So store 1, store 2, and so on and so forth. The day is obviously the day on which people made the purchase. So day 1, 2, 3, 4, 5, 6. Price is obviously the price, 37 units for variety number 1, and sales is the sales per customer, average per customer of variety number 1. So let us get straight into how do we pre-process data, what assumptions need to be met, and how do we write a syntax and interpret results. So this chunk of code essentially attaches this oranges dataset to an object df. Df is data frame, and it is easy to write df instead of oranges, obviously. So the tbl underscore summary. So now we will just look at some descriptives. Let's look at the summary, statistics summary data of this data frame. The tbl underscore summary is from the gt summary library, and it is an extremely useful library where you will get publication ready tables. Just like the ggplot2 or the ggstatsplot library is extremely useful to get publication ready plots, gt summary is extremely useful to get publication ready tables. So look at this, just one line of code and you have a table. It works better if you have groups, if you want to run many association tests together, but it works well for overall data as well. So we can see we have 6 observations per store, 6 observations per day. This is the median and interquartile range for price, and these are the median average number of sales, if you catch my drift. So median average number of sales, so median IQR, right? We are not going to be seeing variety number 2 in this tutorial. So this enables us to get a sense of what type of data we are working with, which is extremely crucial. I always like to summarize my data as medians and IQRs, because I always assume data is not normally distributed, um, and uh, this is a perfectly good measure of central tendency and variance. Now, there are a few assumptions which need to be met, but what I'm going to do is not look at the assumptions right now, but look at them later. So what we will do first is straight away fit a few linear regression models, just simple linear regression models, to our data, and um, then check our linear regression assumptions. So this is the syntax, or rather this is the syntax to run a linear regression. So lm is the function in R to build a linear regression model or a linear model lm. The variable on the left hand side of the tilde, this is the tilde, the variable on the left hand side of the tilde is the dependent variable. So the variable which you are seeing, if it increases, decreases based on some independent variable or predictor variable. So the LHS left hand side is the dependent, RHS right hand side of the tilde is the independent or independent variables. So the first model, we're going to fit just the store, and we are going to see whether uh, the store actually makes a difference in the sales. And um, you always write a argument where you specify the data frame, because more often than not, as you become advanced um, coders, I'm assuming you are not, I may be grossly wrong, please correct me if I'm wrong in the comments, but um, assuming that you are intermediate, as you get advanced, you will most likely be working with lots of data sets, lots of data frames in some projects. So this is a good handy argument if you specify. um, I have attached the data frame, you can see here. So if you attach the data frame, you don't need to specify this argument, because you have attached this data frame to the R environment you're working in, and it automatically recognizes variables from that data frame. But if you haven't, this is a good argument to put. So enough about the syntax for the model. um, this is the first model, and I'm storing it in object fit one, because I want to run many different uh, functions, or I want to get many different uh, data from this model. So as you can see, I've uh, written print, report, and all that. So I want it's better if I store it in an object, and I have done this for the remaining two models. So in the first model, it's a simple linear regression. We are not adjusting for any variables, we're just trying to see the effect of store on sales. Second model, we're trying to see the effect of day on sales. Interesting, which day do people buy oranges more? Monday, Tuesday, Wednesday? It's, of course, it's not written Monday, Tuesday, Wednesday, it's written 1 2 3 4 5 6, but you get the gist. And of course the price, so whether the price of the oranges influence sales. Now and this table UV regression is univariate regression, is amazing. It's a function from the same package GT summary, and you'll see, you're just using one line of code, you'll get a publication ready regression table. So let's run this code without further ado. Right, so you can see that you get a publication ready table. Before we see that table, let us see what we have here. So print gives us the regression model. You can also use summary. I don't like to view this. I like to view the table directly, but sometimes you need to see um, the summary or the report. So you can see here, so we have, with store number one taken as a reference, we see the coefficients for other stores. So as compared to store number one, store number two had lower sales of oranges. Store number 3 had even lesser sales of oranges. Store number 4 had in between those two. Store number 5 had a little better than store number 2, and store number 6 outperformed store number 1 because this is a positive, so it's more, because store 1 is the reference class. Now this was the first fit 1. This is the fit second, so day. So day 1 is taken as the reference class. Day 2 performed poorly. People bought more oranges on day 1 than day 2. Day 3, it was a total orange buying fest on day 3. So on average, people bought 6 more oranges on day 3 as compared to day 1. So if we say day 1 is Monday, then people, went berserk on Wednesday and bought 6 more oranges per person. And this is the same thing on Friday as well. Thursday, not a good orange buying day for the stores. And day 6, Saturday, someone in between. Yeah, weekend people might want to stay at home, go clubbing, what have you. And price. So for variety number 1, you can see that as price increased, sales decreased. So people thought, these oranges are not worth the price. I mean, variety number 1, not worth the price. So as the store owners increased the price, sales decreased. I'm not going to go through the output we got from report of all the fits, because this is quite in detail, and this is especially useful to get all statistics that you need for reporting in one single place. So you can see beta, confidence intervals, the t statistic, p value, standardized beta coefficient, standardized CI. You get R square somewhere here, so 19%, so on and so forth. So you get all that data condensed. Well, not condensed. This is, it's relatively condensed, and you don't have to do any manual work. You have it. Just write report fit 1. You have it. So extremely useful. Now let's come to the good stuff. This is what you'll be publishing, right? This table. So you get all these coefficients, the ones we discussed, in a neat table arranged with beta, confidence intervals, and p values, and the number in case you have missing data as well. Pretty good if you ask me. We spent little to no time and we got all this stuff. But this is a simple linear regression model. These are simple linear regression models, and these do not take into account the effect of other variables in the model together. So this does not take into account the effect of day and price along with store on the model. So what we want is one cohesive, coherent model, assuming that all of these influence each other in some other way, and we fit it in one single model. So I've written the fit all and LM linear model. Sales 1, LHS the dependent variable, remember, and right hand side all the predictor variables separated by plus signs. And do the same thing, report fit all. We can also write summary fit all, and let's run this. Righto, and we also get table. So this is table UV regression because univariate, and this is just regression because we are trying to this is a multivariate regression or a multiple regression. And this last line of code actually merges table 2 and 3. So tables 2 and 3, so we get both univariate as well as multivariate regression results in one single table, as you can see right here. This is what you want to ideally publish in your final manuscript. It's one single table. You don't have to write a lot. Pretty concise and cohesive, and readers like to read that. So let us directly go to this table and see. We already know these results. This part univariate is the same table, so no need to focus on that. Let's focus on the multivariate model. So when the day and the price was kept constant. That's how you interpret multiple models. So keeping the other variables constant. So store 1 actually um, outperformed store 2 outperformed store 1, pardon me, but the result is not significant. Only store number 6 has outperformed store number 1, and this is significant. P value 0.04. All other stores as compared and store 1, performed relatively the same in terms of number of sales, keeping the day and the price constant. But store number 6, I don't know, they might be giving something to their customers when they come in, some personalized service, gift bag, discounts, I don't know. So this uh, a significant positive beta coefficient indicates that this sales were higher in store number 6, keeping the day and uh, price constant. Now day, so like we said, Wednesday people went berserk. Friday people went berserk. you know uh, Adjusting for store and price, wow, almost 10 um, the people bought 10 more oranges than day number 1 on day number 5. So people really wanted oranges on the weekend, it seems. Even on Wednesday, the Friday they bought oranges, Saturday Sunday they eat them, and then again Wednesday, out of oranges. So and the price, you can see it's a significant difference. Also, good way to confirm, the confidence interval does not cross the null value, which in this case is 0, because it's a beta coefficient. If it was a ratio, then the null value is always 1 for a ratio. For example, risk ratio, odds ratios, hazard ratios, so forth. So yeah, people did not want to pay more for variety number 1. Lower price of oranges uh, indicated more sales, keeping day and store constant. So, oh, now for the assumptions. So now we are done fitting the models. Okay, so the models fit well. Let's see the R squared value. So what's the R squared? So R squared is the uh, uh, how much the predictors explain the dependent variable. So 0.73 or 73% is a pretty high R squared value. So this model explains 73% of the variance in sales of oranges. That's a high R squared. So this is a very well fitting model, and this explains, so the predictors that we chose explain the dependent variable or the sales pretty well. So if you are a store owner, you would most likely want to concentrate on these factors. So of course you can't control the store that you have. Say you are stuck with a bad store. For example, let's see which store is store number 3, I guess. Store number 3 um, is not performing very well. So instead of just sitting around crying, you can focus on the price. So keep a competitive price, or strategically choose days on which people like to buy oranges. So um, provide discounts on Wednesday and Friday. So this is pretty interesting, because with these insights you can actually increase your business, increase your sales. Now I am a doctor, I am a healthcare professional, and we use this all the time in making healthcare decisions. So do many other business owners. Um, but this is pretty interesting, and this is the power of data. The data gives you actionable insights and how you can leverage existing parameters to increase output. Now, this was the exciting part. Now let's go to the assumption checks. Not exciting, but important. So these statistical models assume certain characteristics of the data to hold true to make decisions. So if these assumptions are not fulfilled, then it might not be right to use these tests. Most of the times you will find one or two assumptions that are not met. There are workarounds around those assumption checks. Um, and there are different models, robust models that you can use, but it is important to check model assumptions at the end. I would suggest at the end, uh, because then you already know, have an idea of how, what um, conclusions you have from your data, so you can build models strategically um, tailored to fit to that data. Right. So the first assumption for linear regression is linear relationship. There exists a linear relationship between your dependent and independent variables. So very easy. Just plot a graph. Just plot a graph. It's very easy. And the ggstatsplot package. I'm sorry. The ggpubr package provides the ggscatter function to do this. Just one line of code. So do this, and you can see. Um, so, oh, uh, we only want price 1. Okay, so we can see that so there exists a linear relationship with, you know, pretty narrow confidence interval. So yeah, this assumption I would say is met. You can see a negative um, regression line with confidence intervals which are not too wide. So I would say okay, this seems like a linear relationship. Now the residuals are independent, and there should be no correlation between consecutive residuals and time series data. So that means you should not have dependent data. So what do I mean by that? Data for one single, say, sales or one single person should not be repeated. There should be no dependency. Every um, observation should be independent of the other. That's it. That's what's meant by independence. Homoscedasticity. The residuals have constant variance at each level of dependent variable. Just plot the fitted values with the residuals and see if the variance, that is a spread, is the same throughout the fitted values. So I would say this is the residual. So by spread I mean how much it is spread vertically. So I would say yeah, the spread at this level 10 to 15 is relatively higher, but I would not say there is a very skewed or very um, you know drastic difference in variance. I would say this assumption, I would not say this is a very this assumption is not met. I would say this is fine for our model. So in statistics, it's a very important thing to know when to be lenient and when to be strict. And data visualization techniques, although subjective, are extremely important and the most useful, um, because you are the best judge of how your data is, and um, you should not decide on your model just based on the results of one objective test. Although it has its place, I'm more of a subjective guy, um, and I prefer visualization methods more than objective techniques. And the fourth assumption is that of normality. So plot QQ plot, quantile plot, theoretical versus sample quantiles, and the thing which you need to see is whether all these points conform to this line that is drawn. And I would say in the middle, it most of the data sets, at the end, so at the extremes, outliers, extremes of the distribution, they are outliers. They will not, more often than not confined to this line. So I would say okay, I mean, the the data in the middle is conforming to this line more or less, but at the end, one or two, 1 2 3 4, they are not strictly fitting onto this line. But I would say it's fine. This is more or less a linear QQ plot. It's fine. And multicollinearity, this is the general variance inflation factor, GVIF, or just the VIF, variance inflation factor. And rule of thumb, these should not be more than 5. If they are more than 5, then one or the other variable is highly correlated with the other variable, and that means if you have multicollinearity, drop one of the correlated variables. You don't need two variables which are measuring the same thing, right? For example, if you are, say, measuring um, systolic blood pressure and diastolic blood pressure, for example, more often than not, they will be correlated with each other. So, in this case, either use SBP or DBP, or use a mean arterial pressure, combining both these variables into one. So, get rid of that multicollinearity, get rid of two redundant variables or one redundant variable, combine it or exclude it, and use the most important or combined variable. So, this was a long tutorial, but I hope it was interesting, and you learned how to do linear regression in R. Uh, Please do check variety number 2. It has some interesting findings. Comment down in the comment section what interesting findings you get, and adios.